Hi, this is Christina, inviting you to come and join me.
Welcome back, friends, to the Deep Dive, the program where we uncover the hidden twists and turns behind the technology shaping our everyday lives. Even when you think you've got something all figured out, there's often a detail or two lying in wait, ready to surprise you. Take your trusty AI chatbot, for example. You might figure that if you asked ChatGPT the exact same question twice, under the exact same conditions, you'd get the exact same reply. And yet, have you ever tried it with the temperature cranked all the way down to 0 so it should be steady as a rock, and still noticed small changes in its answer?
Sure, I think most folks have run into that at some point.
And what happened? More often than not, you saw a reply that was just a touch different, maybe only subtly so. Makes you wonder, why isn't it identical? Aren't computers supposed to be clear-cut, delivering the same output every time for the same input?
It's a first-rate starting point, actually, because that little bit of variation really does challenge our basic notions about how digital systems operate. It's the very mystery we'll be unwrapping today.
We'll begin with two key parameters you can use right now: temperature and seed. These give you a measure of control over just how creative or consistent your LLM's output will be.
Right, the main adjustment knobs most people recognize.
Yes, but here comes the surprising part. Even when you try to make an LLM completely predictable, achieving true bit-for-bit determinism can be downright elusive. This opens the door to some deep engineering challenges.
Absolutely, and our mission for you folks is to equip you with the know-how to navigate the whole landscape.
Yes.
You'll not only learn how to adjust creativity and consistency, but also peek into how leading researchers are stretching the boundaries to achieve true reproducibility.
And in the process, we'll uncover some fascinating complexities lying just beneath the surface. All right then, let's unpack this. Before we even get to reining in randomness, we need a primer on how these LLMs actually pick their words.
Good thinking.
Picture this. The model has a vast vocabulary, and for each word it considers next, it assigns a probability. It's like scanning a giant menu, with each choice having a different chance of being picked.
That's right. It's essentially reviewing all possible next tokens. Tokens that could be words, parts of words, or punctuation, and deciding which one to take. And generally, there are two principal ways the model chooses.
Okay.
First, there's greedy search. Very straightforward. The model picks the token with the single highest probability every step. No surprises, just a top dog each time.
So if that part of it is most likely, it picks that every single time. Simple as pie.
Exactly. The other approach is sampling. Here, the model picks a token according to the probability distribution, almost like rolling weighted dice.
So not always the top candidate.
Right. Take a fun example from our sources, the Chuck Norris one. If you ask, what's the favorite dish of Chuck Norris? Maybe dynamite scores a 58% chance, and venom gets 29%. With sampling, you might actually land on venom, even though dynamite is more likely. It adds a touch of chance, but in a calculated way.
So, if we're not always taking the highest scoring word, how do we guide just how much chance is in play? That's where creativity control comes in, right?
That's right. We use something called temperature. It's like a dial that makes the model either more adventurous or more conservative. Temperature essentially scales the raw probability scores, called logits,
Yes.
before the model makes its pick.
Scales them, but in what way?
Say you set a low temperature, like 41. This magnifies the differences between probabilities. The highest one becomes even more dominant.
Peakier.
Right. That pushes the model toward very predictable, almost deterministic results. In our Chuck Norris scenario, at 41 temperature, dynamite might rocket up to 99.9% likely. The model plays it safe.
So, low temperature for factual, straight-to-business answers. Makes perfect sense. But what if you want the model to stretch out creatively?
Then you crank it up maybe 2.0. This flattens the distribution so those lower probability options have a fighting chance.
So choices become more evenly matched?
Relatively speaking, yes.
Yes.
Outputs become more varied and creative. but as you'd guess, sometimes less coherent. At 2.0, dynamite might drop to 40%, letting Venom or even himself become plausible picks. You've dialed up the randomness.
Alright, temperature sets the level of randomness. But suppose you want that creativity and the ability to get the same created outputs every time. Sounds like a contradiction. Randomness that repeats.
It sounds that way, but it's not, once you bring in the seed parameter.
Yes.
This is the gateway to reproducibility.
Ah, the seed.
Exactly. A seed sets the initial state of the random number generator used during sampling. Think of it as specifying exactly how to shuffle a deck before dealing.
Right. A fixed starting point for everything that follows.
Precisely. So if you fix the seed, say to 42, then even at high temperature, your random selections will be identical on every run.
Every time.
Every time. Same prompt, same settings, same results.
I see how that's handy.
Oh, it's essential. For debugging, testing, and making sure that changes in output come from your adjustments, not chance.
And without a seed, that consistency, poof, just vanishes.
Completely. Without a fixed seed, outputs will differ run to run, even if temperature is held steady. That same, tell me a joke about dogs prompt might start with sure in one run, maybe why in another. Without a fixed starting point for randomness, you're at the mercy of chance.
Got it.
One caveat, even with a seed, some big commercial outfits like OpenAI won't promise bit-for-bit identical results.
Oh? Why is that?
Because they might change underlying model configs or infrastructure behind the curtain. They do offer a system fingerprint, so you can track whether background changes happen between runs.
Alright, that's good to know. And we should tip our hat to other parameters too, right? Like top K and top P sampling.
Yes, definitely worth a quick nod. These let you refine which tokens the model samples from after temperature is applied. Top K means pick from only the K most probable tokens.
So, say, only choose from the top 10.
Exactly. And top P is a touch different. It includes the smallest set of tokens whose probabilities sum to a chosen P. Maybe all tokens that together reach 90% probability. Just more levers to balance creativity with coherence.
More knobs to turn.
That's the ticket. So for practical use, want the most deterministic output possible, set temperature to 0, that forces greedy search.
Right, the top choice every time.
Yes. For creative but reproducible results, use temperature above 0 and set a fixed seed.
Okay.
If you want wildly different results every time, skip the seed entirely. Let the model roam.
So far, so good. Temperature and seed give us neat control. Seems we have it all wrapped up.
It sure seems that way at first glance.
But here's the twist. Even with temperature 0 and a fixed seed, research shows you might still fail to get identical results. With commercial LLM APIs or even open source inference libraries running on your own hardware. Why is that?
This is where it gets interesting, and counter to how we picture computers behaving.
Yes.
We think of them as always giving the same answer for the same input. And reproducibility is a bedrock principle in science. Yet in LLMs, achieving it can be surprisingly tricky, even when you're trying your level best.
My first suspicion, and I'm sure I'm not alone, is GPUs doing floating point math. You know, numbers not being represented perfectly, and parallelism mixing things up. Is that the culprit?
That hunch has a kernel of truth, but it's not the whole picture. The math term is floating point non-associativity.
Non-associativity.
Right. It means A plus B plus C may not yield exactly the same microdecimal result as A plus B plus C, because finite precision and rounding errors sneak in.
Ah.
For example, adding a very small fraction to a huge number, then subtracting the huge number, might give a slightly different result depending on the order. The classic example is 0.1 plus 1e20, then minus 1e20. You might get 0 when you should get 0.1 if the ordering shifts.
So at a low level, yes, tiny numeric differences are possible.
Absolutely. But here's the surprise. That's not the only or even primary reason for non-determinism at temperature 0.
Oh?
Most GPU kernels, the building blocks that do matrix multiplies and such, are built to be deterministic. Give the same kernel the same input, it'll give you the same output every time. Engineers have solved that part for most forward pass steps.
Okay, so if the bricks are deterministic, why isn't the whole house?
Because of something called batch invariance, or rather the lack of it.
Batch invariance, what's that?
When your prompt hits an inference server, especially a busy one, it's often bundled with other people's prompts into a batch for efficiency.
Makes sense.
The twist, your answer can change depending, subtly, on how many other prompts are in your batch.
Wait, why would running others' jobs alongside mine change my result? Shouldn't the math be independent?
You'd think so, but from your viewpoint, that batch size is an unpredictable external factor. If kernels aren't perfectly batch invariant, meaning they don't produce the same answer no matter the batch makeup, then differences creep in even at temperature zero.
Wow.
And it's not just GPUs. CPUs, TPUs, you name it. It's a parallel processing issue tied to reduction operations.
So the ideal is same input, same output every time, no matter the batch or server load.
Exactly.
How do engineers beat this ghost in the machine and make batch invariance happen?
By making every computational step batch invariant. Straightforward ops like adding a constant everywhere are fine. The trouble comes in reductions, summing or finding maxima across numbers, inside RMS norm, matrix multiplies, attention.
Combining many values down to fewer.
Yes, and the order of those operations can change with batch size. Since we know floating point math is non-associative, that change breaks determinism.
So to fix it, you force a single computing path for every batch size.
Exactly. Like setting a factory line to always build your car in the same step order, even if there are 10 other cars on the line. It might mean a tiny slowdown for big batches, but you get consistency.
So RMS norm and matrix multiply get locked into one calculation order.
Yes, overriding adaptive behavior that might otherwise tweak the path for different batch sizes.
And attention.
That's the trickiest. Attention does multiple matrix multiplies and sums on both the feature and sequence dimensions. Two big challenges. First, managing the KV cache, the model's memory. The order it's accessed must never shift with batch composition. Solution, update the cache and page table before the attention math begins.
All right, and second?
During decoding, generating tokens one by one, systems often split the cache dimension for speed. But if you alter the number of splits to match current workload, you change the operation order, breaking invariance. The fix, use a fixed split size each time, regardless of load. That way, the math path stays identical.
Remarkable. So all variability tied to batch size is engineered out.
Exactly.
After all that trouble, what's the payoff? Is it worth it?
They tested it with the Quen model. Temperature, prompt, tell me about Richard Feynman. Generate 1,000 tokens, run it 1,000 times. Without batch invariant kernels, 80 different completions. First divergence popped up at token 103. Most said Quen's New York as birthplace, but 8 said New York City, all from batching non-determinism.
Incredible.
With batch invariance on, all 1,000 completions bit for bit identical.
Okay.
Exactly the mathematical expectation at temperature zero, proven by engineering.
Compelling. And speed.
Initially, deterministic ran slower, 55 seconds versus 26 seconds for VLLM default. But with optimization, especially better batch invariant attention, they cut it to 42 seconds. A gap, but not insurmountable.
Encouraging. And determinism matters beyond this, like an RLHF train.
Absolutely. In RLHF, if the model used for sampling differs ever so slightly from the one used for reward calc, you get off-policy learning by accident. Like teaching from one textbook but grading from another, the student gets confused. Training destabilizes, the reward signal can collapse.
Yikes.
With bit-identical results, the KL divergence between training policy and sampling policy is flat zero. You get true on-policy RL. Smooth, stable, effective. That's the breakthrough.
So controlling LLM output isn't just about temperature and seed.
Right. Those are important, but not the full recipe for true predictability.
True bit-for-bit reproducibility means tackling floating point quirks and batch invariance.
Same computation path no matter the batch or server load.
And whether you're a user, dev, or researcher, understanding why LLMs change answers matters.
Absolutely. It's about trust, reliability, and rigorous science, leading to safer application.
It sure makes you appreciate the complexity hidden behind what feels like a simple chatbot reply. Looking forward, if we can achieve perfect determinism, it could reshape how we evaluate, trust, even regulate AI in high-stakes work like medicine or finance.
That's a profound thought.
Makes you wonder if our expectations about AI's unpredictability we'll need a serious reset in the years to come. So, until next time, keep asking the questions and never be shy about taking a deeper dive. The deeper, the better.
Hope you enjoyed listening to, well, my voice. If this was useful, hit subscribe and share it with a friend. And there's a little extra for you in the show notes or description.